All right, let's see if I can full screen this. All right, let's get started. So welcome everybody. I see about half the class has already joined us. I'm going to assume that give it a couple minutes and the rest of us will be joining soon. Just a couple quick announcements. So homework 6.1, I went ahead and graded that. That is graded on Blackboard. So what I did is if you check Blackboard, you should see individual grades for your assignment. And then I also posted on Microsoft Teams just some general comments on the assignment as a whole. And I might continue to do that just to, A, reduce the amount of email traffic that you're probably getting, and B, just to put all the comments in one place. So for instance, if you're studying for an exam, all the common comments are all going to be in a single place. Homework 6.2 is due. I'm going to be pretty, I don't want to say super lenient on the homework being late, but for instance, if the homework is due on Wednesday, I probably won't start grading it until Thursday. So as long as I have all the assignments there, I'll be fine on assigning late penalties and things like that. So just do me a favor and try and get it submitted as soon as you can. I'll probably grade those either tonight or maybe sometime tomorrow. I want to talk about the schedule for the next few days. Now, we are scheduled to have an exam on Monday. I had an email from one of the students in the class that there was an exam in environmental also on Monday, but I think that exam in environmental is supposed to be getting pushed to Wednesday, so we'll still be able to do ours on Monday. For those of you that are in steel design, the exam is going to be very similar to what we did in steel design. I'll open the exam at 4 p.m. It'll close at 7 p.m. So that'll give you 3 hours to do the exam and upload your calculations. But it's not a 3-hour exam. It's going to be it's designed to be a 50-minute exam, just like we would do in class. Again, 5 conceptual problems, 3 computational problems. Again, just like we've done in class. So you'll have plenty of time to do the exam, to upload your calcs, and hopefully to account for any technical glitches. I'm going to have a homework uploaded based on today's lecture, but because we have an exam coming up, I'm not going to have that homework due until Wednesday. So you'll have plenty of time to do that as well. I thought I would also mention the updated grading policy. I'm sure it's the elephant in the room, as it were. So you all, well, thank you. Yeah. I saw your comment there, Farrah. I don't think that most of the people in steel design had an issue with. I don't think time was a big issue in steel design. As the exam was going on, I was periodically checking, and most people got it done in time. Now, I'm going to make the exam incredibly difficult based on what Mr. Schwartz just said in chat. That was a joke. I still have jokes. I'm still going to throw some jokes out there. Now, let me just really briefly mention the grading policy. So you all probably saw the email that students can opt in to credit, no credit. I saw that comment, Mr. Schwartz. You have until April 24th to do so. So my first piece of advice would be, regardless of whether or not you're deciding to do this or not, I wouldn't worry about doing it right now. You have plenty of time to figure out whether or not you want to do that. The credit, no credit won't affect your GPA, so that's probably going to be where my primary piece of advice would go. But the big thing to keep in mind is that regardless of whether or not you opt into credit, no credit, the classes still continue on as they were. So we're going to still press on in all of our classes, you know, as everything is going. So, I mean, we're still going to have our exams, still going to have our homework assignments, what have you. The policy also stated that your college, if you will, might have drafted supplements to that. Engineering hasn't drafted anything yet, so as far as I know, the university policy is what it is. My advice to you as to whether or not you're thinking of opting into credit, no credit, is it's really just a function of your GPA and what you think is going to happen. Like, for instance, if you have like a let's just keep the math simple. Let's say you have a 3.5 GPA. If you think you're going to get all A's, then don't opt in, because all the A's are going to do is raise your GPA. If you have a 3.5 GPA and you think you're going to get all C's, well, C's are going to lower your GPA. So I think that's really the only thing you need to keep in mind. That I don't know that I have any better advice. I don't know that I have any better answers. I do want to make sure that we're being cognizant of the lecture. So if anybody has any questions about this, you can email me. I would also make sure that if you have any questions, contact your advisor. Your advisor, I mean, that's our job. So if somebody wants to opt in, do you email the professor? I don't believe so, but I think the university's still figuring that out. I believe it's an opt-in through the registrar's office that you would contact the registrar. As I understand, the professors don't really even have anything to do with it. We just keep pressing on, and you decide what you're going to do. But again, to be absolutely clear, I don't think there's any real rush to do it now. I would wait until you've had a chance to talk with your advisor and figure out what's the best option for you. So, but no, I don't believe that you email your professor. But yes, homework 7.1 is due on Wednesday, April the 8th. So it's not due Monday, and I'm not going to have it due Monday because we have an exam on Monday. So I don't want to have two things due at the same time for you. Any other questions about logistics? All right, I'm going to go ahead and get into it. So today, we're finished with shear design, and to be clear, exam 2 stops at shear design. So what we're talking about today is not on exam 2. Exam 2 covers T-beams, doubly reinforced beams, and shear. Today we're going to be talking about serviceability. Okay, and serviceability for us is going to be a fancy way of saying we're going to be talking about deflections. Okay, now I mentioned the word serviceability, so I want to kind of explain what I mean by that. In structural engineering, first off, I want to briefly recap the term limit state. We might have mentioned that here and there, but a limit state is a condition that we as a structural engineering community define that structures have to satisfy. So a common set of limit states, for instance, are strength limit states. They're intended to ensure the safety of the structure. And so we've been dealing with strength limit states all semester. So for instance, moment capacity. We use factored loads. We do 1.2 dead, 1.6 live to get a factored moment. And then our phi-mn, our factored resistance, has to be greater than or equal to that factored load. And as long as the factored resistance is greater than or equal to the factored load, then we've ensured safety. And that's what those factors are. They are safety factors. You have load factors, 1.2 for the dead, 1.6 for the live, and then you have safety factors for the resistance. You have these phi values, like it's 0.75 for shear, or, it can be 0.9 for bending, or it can vary depending upon your strain and whatnot. But that's what a strength limit state is. A strength limit state is intended to ensure that the structure is safe, that it's not going to fall down and kill somebody. Service limit states are a little different. Service limit states aren't really about safety. They're dealing with just the day-to-day performance of the structure, like making sure the structure doesn't deflect too much, or that there's not too much corrosion or vibration or things like that. So they're not a safety issue, okay? So because of that, and for the next couple of weeks, I want everybody to hear what I'm saying. For the next couple of weeks, we're not going to use load factors. So no 1.2 times the dead or 1.6 times the live. We just deal with the raw loads, just dead plus live. Now, I know we've got I know we have to deal with social distancing, so I can't do this, but if you feel yourself wanting to do 1.2 dead plus 1.6 live, just slap your hand and say, no, don't do that. Remember, no load factors for what we're doing for the next couple of weeks. So anytime we're dealing with a service limit state, nothing's factored. Now, for our purposes in the class for serviceability, what we're going to be dealing with and what we're going to be concerned are deflections. Okay, controlling deflections is one of the most important tasks that we deal with in design, and because if a beam or an element deflects too much, it doesn't mean that the structure is going to fall down and kill somebody, but it can result in performance that you wouldn't desire in a structure. So, for instance, if you've ever been in a building that has a plastered roof, like the roof has plaster on it, one of the reasons that we have deflection limits is intended to ensure that, for instance, the plaster doesn't crack. So if the beam deflects too much, the plaster will crack and the structure isn't performing the way it wants to. Now, if the plaster cracks, that doesn't mean the structure is going to fall down and kill somebody, but we obviously don't want that to happen. So those are limit states that we have to assess. Some other limit states or some other events that can happen when you have serviceability issues, one of them is ponding. And so I have an image here on the left that kind of explains what ponding is. So this is looking at the roof of a building. And so if you have a beam that deflects too much, what can happen is you collect water in a given region of the roof. Well, water isn't weightless, it has load, it has weight to it. So as it collects water, it collects load, and so that load causes more deflection, which causes more water to accumulate, which causes more deflection, which causes more water to accumulate, and it sort of builds on itself. That phenomenon is called ponding in the world of structural engineering, and so that's something that we would obviously want to avoid. Also, we might have issues with cladding or facades, like the image on the right. If your support beams deflect too much, maybe the cladding wants to fall off. And so it doesn't mean the whole building's coming down, but it's obviously something that we wouldn't want to see exhibited in our structures. So deflections are arguably one of the most important serviceability related issues that we deal with in structural engineering. Now, let's take a blast from the past and let's go back to structural analysis. So if you want to compute deflections, there's a couple of ways to do it. The first way is to actually go through and derive it, and that's using the principle of virtual work. So does everybody remember that formula there in the gray? I know it's been a while since you've seen that, but that's how we would determine deflections in structural analysis. We would take the real moment function and the virtual moment function, and then we would integrate it across the entire span, and our deflection would be the sum of those integrals divided by EI. Okay, remember, E is the modulus of elasticity, and I is the moment of inertia. Another thing to remember is that because we deal with typical U.S. customary system units, we have our loads and our member dimensions that are usually in kips and feet, but then our section properties, like our modulus of elasticity and our moment of inertia, are in inches. So we have to throw a unit conversion there. And if you remember in deflection land, our conversion factor was 1728, because remember we had to convert cubic feet to cubic inches, so 12 times 12 times 12. So that conversion factor is going to come back up. Now, in here, I'm not really going to make you do the integration. We did all that last semester. So in here, we're going to be able to use some pre-derived formulas. If you go to Blackboard, if you remember, we've seen this this design aid before. There's a PDF. It's the first supplement, the first design supplement, and it has oodles of those different cases. You know, if you have a distributed load or you have a concentrated load or whatever. This here is if you have a simply supported beam and you have a load at midspan. And if you look, I know it's a little small here, but if you look at the maximum deflection, that's going to be at midspan at where the load is, and it says the formula is PL cubed divided by 48 EI. So if you had a beam with a load at midspan, you could just plug and chug into that formula and it would give you the deflection. Again, don't forget the 1728. We'll still need that to make our units copacetic, to make them make sense. But the big takeaway that I want to talk about today, this is really all I'm interested in talking about today, is that I don't care what method you use to compute deflection. In order to compute deflection for a beam, you need some E value and some I value. You have to have a modulus of elasticity for the concrete, and you have to have a moment of inertia. Now, the modulus of elasticity is really simple. Okay, we've actually seen this before. We used this a while back when we were looking at flexural analysis. So recall the expression. It's 57,000 times the square root of FC prime for normal weight concrete. And then there's this formula above for if you're dealing with any concrete between 90 and 60, or 90 and 160 pounds per cubic foot. That's going to be our that's going to be our formula. Again, plug and chug. Don't forget that whenever you're when you're computing deflection, or sorry, when you're computing these values, you have a square root of FC prime. Put in PSI, get out PSI. All right. So the E value is really simple. What is a little more challenging is the moment of inertia. Okay. And the reason why is what's going on in this slide. Okay. So let's look over here on the right. Let's say I have a simply supported beam and I have a uniformly distributed load. So I would hope that if that's the case, everybody would agree that the moment diagram looks something like you see here below, that image B, that you have a parabolic moment diagram. Okay. Well, remember, let's go back. Let's sort of go back in a time machine back to like January and February, and let's talk about the cracking moment. Remember, we have 3 stages of concrete beam behavior. We have its uncracked behavior, its cracked behavior, and then its behavior at the ultimate capacity. And remember, whether or not a beam is uncracked or cracked is whether or not the moment is larger than MCR, than the cracking moment. Well, if you look at your moment diagram like this, the ends have a bending moment of 0, and the maximum bending moment is at midspan. Well, if that's the case, then it's feasible that some of your beam is possibly cracked and some of it isn't. So, for instance, if you look at if you look at image C, see how the cracks are in that central region. They're in that region everywhere that the bending moment is larger than the cracking moment. So if you look at your beam analytically, you've got a situation where some of the beam is cracked and some of it isn't. So if some of the beam is cracked and some of it isn't, what moment of inertia do you use? Do you use the gross moment of inertia, or do you use the cracked moment of inertia? And the answer is neither. You basically use a value in between. And so ACI allows us to use a plug and chug expression called the effective moment of inertia. Okay. Now, this yellow box here, that's the formula for the effective moment of inertia. I will go ahead and tell you that if any of you all have friends who took this class last year and you've got their notes or whatnot, I'll tell you this formula is completely different. ACI released a new specification in 2019, and this is the new formula for the cracked moment of inertia. That formula, the old formula, had been in place for like 55 years, and they finally updated it to reflect the physical behavior of the beams a little bit better. So this is our new formula for the effective moment of inertia. It serves the same purpose. Instead of using the full-blown gross moment of inertia or the cracked moment of inertia, it's kind of somewhere in between. It's like a weighted average. And in order to compute this value, you need 4 quantities. You need a gross moment of inertia, you need a cracked moment of inertia, you need the cracking moment, and then you need the applied moment. Okay, now we'll talk about specifics with the applied moment on Monday. I'm just going to give you a value for our example today. But just keep in mind, there's no load factors. It's just service loads, no load factors at all. Now, you only use the effective moment of inertia when the applied moment is greater than about 2/3 of your cracking moment. Otherwise, you would just use IG. But don't worry, we're going to recap what all these terms are. I know it's been a while since we've looked at a lot of this. That's sort of the purpose of today. Now, let's see. So we have a gross moment of inertia, a cracked moment of inertia, a cracking moment, and an applied moment. Let's start off with the cracking moment. If you look over here in the gray box on the bottom right, remember, how do we compute the cracking moment? We take FR times IG over YT. That's our formula for the cracking moment. And then FR is 7.5 times lambda times the square root of FC prime. It's probably been a while since we've seen a lot of this. Or probably been a while to a lot of you, and that's sort of the purpose of today, is to get a recap for all of this. Now, I wanted to recap some of these terms. So the gross moment of inertia and YT. The gross moment of inertia is really, really simple. If you have just a rectangular beam, it's just BH cubed over 12. And then YT, remember, YT is the distance from the centroid to your extreme fiber in tension. So for a rectangle, that's just H over 2. Now, if you didn't have a rectangular section, you'd have to use the parallel axis theorem. What I did here on this slide is I actually set up the table, and if you look, I put all the formulas in the cells so that you wouldn't have to remember, like, well, what do I do here, or how do I compute that? I wanted to make it as easy for you as possible, so all the formulas here are plug and chug, okay? But again, if you're dealing with a rectangle, you don't have to worry about all this. Just bh cubed over 12, super easy. Now, the cracked moment of inertia, now, this is where you take the beam that's intact, and remember, once you exceed the cracking moment, it looks like what you see here on the right. Okay, it looks like this part right here. So remember, we assume that all the concrete above the neutral axis is intact and all the concrete below the neutral axis is gone. We turn this steel into an effective lump of concrete, and we do that through this modular ratio. So the modular ratio is right here. That's just ES over EC. Now, don't forget, ES is 29,000 KSI. That, again, I'm going to burn that number into the back of everybody's head when this is all said and done. As for solving for your neutral axis, again, I just made it easy for everybody and put the formula right there. And then here's the method for computing your moment of inertia. And again, I just threw all the formulas in here for you to make it as super easy for you as possible. Now, all I care about is your ability to compute ICR for a singly reinforced beam. If we ever have to deal with a doubly reinforced beam or a T-beam, I can provide examples if you want, but I'm really not going to worry about that with what we've got going on with our distance learning. If we need those values, I'm just going to give them to you, and I might post an example on how to do it. But don't worry, I'm not going to make you do that. The only thing I'm going to make you worry about is for a singly reinforced beam, and again, we've dealt with those before. So I have here an example, and all I'm concerned about is just computing the EC and the IE value for this beam shown if the applied moment is 140 foot kips. So FC prime is 4 KSI. Notice I didn't even tell you what's going on with the steel. It doesn't matter for either of these values. All we need to know is that it is steel, and so steel has an E value of 29,000 KSI. Make sure and express your E value in KSI when it's all said and done. It's 14 inches wide, 24 inches deep, and it has 4 number 9s. And so let me go ahead and get some things set up. But while I'm getting this set up, does anybody have any questions before we jump right into this? Okay, so let's just jump right into it. Okay, so here's our problem, and if you notice here, I've got a lot of the values already chugged out for us. We have that FC prime was 4 KSI, and again, also, oh, hold on, let's see, we know that it's normal weight concrete. So normal weight concrete tells us that lambda is 1.0. We also know that MA, our applied moment, is 140 foot kips. Okay. All right, and I think that's everything we need to go ahead and just start rocking and rolling with this. So again, I think you're going to find that this is very, very straightforward and very plug and chug. So I'm going to get right into it. And so the first thing I'm going to do is I'm going to compute the gross moment of inertia. And so that's just IG, which is BH cubed over 12. Now again, if this was anything other than a rectangle, we'd have to go through and figure it out. But because it's a rectangle, this is just a very plug and chug expression. And so B in this case is 14 inches. H is 27 inches, and that's cubed over 12. And so 14 times 27 cubed over 12, once you plug and chug that out, comes out to 22963.5 inches to the fourth. That one's pretty easy. Okay. Next, what we're going to do is we're going to compute the cracking moment. So in order to do that, we need three quantities. So the first thing we need is FR, which is 7.5 times lambda times the square root of FC prime. So that's 7.5 times 1, since this is normal weight concrete. And then remember, square root of FC prime, you put in PSI, you get out PSI. So this is 4,000 PSI. And so 7.5 times 1 times the square root of 4,000, that ends up being 474.34 PSI. One thing, again, during chat, if I'm going too fast or if there's anything that has got a hiccup, you let me know. Okay, make sure and keep me apprised. And if you got any questions, please don't hesitate. All right. We need IG, but we literally just computed that, 22,963.5 inches to the fourth. And then YT is H over 2. And again, that's because it's a rectangle. If it was a T-beam, we'd have to use we'd have to compute the centroid. I mean, H over 2 is the centroid for a rectangle, but just keep that in mind. So it's 27 inches over 2, and 27 over 2, that's 13.5. So therefore, the cracking moment is FR IG over YT. And so that's 474.34 PSI times 22,963.5 inches to the fourth. And then YT was 13.5 inches. And so that comes out to be, it's a pretty big number. It's 806,855.14 inches. Sorry, hold on. So that's the, hold on, let me take a step back. So when you plug and chug the value, you get 806,855.14. Okay. Now, this is a moment. Okay. When you looked at the expression, you plugged in pounds and inches. So because this is a moment, this is inch pounds. Okay. Converting this to foot kips. Does anybody remember in chat, what's your conversion factor to convert a moment from inch pounds to foot kips? I want to see if anybody remembers. 12, exactly right. You divide by 12,000. I'm going to scroll this up a bit so I have some room. So, yeah, because it's 12,000 inch pounds is 1 foot kip. So if you take that value and you divide it by 12,000, you end up getting 67.24 foot kips. Exactly right. Okay. Now, what I'm going to do here is just to make sure that we're tracking the values that are really, really important. When you compute a effective moment of inertia, you need 4 quantities. You need a gross moment of inertia, so that was 22,963.5. Let me see if I can clean that up a bit. Let me sort of underline that to say, okay, that's a critical quantity that we're going to need. You need a cracking moment. You need an applied moment. We were given the applied moment, and in this problem, it's 140 foot kips. You also need a cracked moment of inertia. So I'm sort of off to the side just saying, okay, these were the critical values that I needed for the problem, just to make my bookkeeping a little easier to handle. All right, so we're 3 for 4 because we have the other one. So next we need the cracked moment of inertia. All right. Okay. So the first thing that we need to do to compute the cracked moment of inertia is we need a modular ratio. We need an n value. Now, in order to compute n, we need ES over EC. So let's go ahead and compute EC first. This is normal weight concrete. So normal weight concrete is 57,000 times the square root of FC prime. That'll give us EC. And so this is 57,000 times the square root of 4,000 PSI. And when you plug and chug that out, it's a big number. It's 36,04996.53 PSI. Or if I'm turning that into KSI, I just divide by 1,000. And so dividing this by 1,000 comes out to be, we'll just say it's 3605 KSI. And remember, that was actually one of the things that we had to compute in this problem. The problem asked for EC and IE. So I'm going to report that in the end as our final answer, but I'll wait and do that later. Right now, I want to use that to determine what is N. Okay, and N is ES over EC. Again, ES 29,000 KSI over 3605 KSI. And when you chug that out, you get an N value of 8.04. And whenever we deal with N values, we just round to the nearest whole number. So I'm just going to take N to be 8. Okay. All right. Now, in order to compute a cracked moment of inertia, we need to know where our neutral axis is. So remember, we use that formula b over 2 x squared plus NAS times x minus NASD is 0. And so b over 2 is 14 over 2, which is 7. NAS is 8 times the area of steel. This had 4 number 9s, so it has an area of 4 square inches. So that's 32. And then NASD is 32 times D, which was 24. And so that comes out to be 768. So therefore, we have a quadratic equation that's 7x squared plus 32x, and then it's minus 768. Okay, don't forget that last term is negative here. Now, I'm assuming that everybody here can solve a quadratic equation. When you solve this out, you get 2 answers. So again, you know, negative b plus or minus square root of b squared minus 4ac all over 2a. You get 2 answers. You get x1 and x2. x1 is minus 13.01 inches, and this is positive 8.44 inches. So of these two, remember, you're solving for a neutral axis and a beam, so you only take the value that makes sense, and so the value that makes sense is the positive answer. So x is x2, which is 8.44 inches. All right. Everybody good so far? All right. And again, if you got any questions, please, don't hesitate. Throw them in chat. All right. Now we need to compute a cracked moment of inertia, so I'm going to draw a table out. We have two shapes. We have the concrete. We have the steel. All right. So we don't have to determine where the centroid is because we already know that's what X is. So all we need is an I value. We need an A value and a D value. So this computation is a bit shorter than if we had to start from scratch and figure out where the centroid is. So for the concrete, remember, if you go back to the slideshow, I mean, we did this, earlier in the semester. And so in the slideshow, I just gave you what these formulas are because we've already derived them before. Remember, this is bx cubed over 12. So that's, what is that, 14 times 8.44 cubed over 12. And so when you chug that out, you get 700.23. And that's for the concrete. For the steel, if you remember, the steel does not have a moment of inertia. It's just zero because it's just a lumped area at a specific point. So there's no real dimensions to figure that out. But it does have an area. The area of the steel is just NAS, which is 32. 32, not 37. And I'm foregoing units because it's there on the top of the table. All these are, for instance, in square inches. The area of that box of concrete is just B times X. So BX is 14 times 8.44, which is 118.09. 118.09. D. So for the concrete, that's just X over 2. So 8.44 over 2, which is 4.22. And then for this, it's just D minus X. Okay. And so this is, what is D? D was 24 inches minus X. So 8.44. And that's 15.56. All right, and so now that we have each of the quantities that we need, we say I naught plus AD squared. And so for the concrete, we just take that plus that times that quantity squared. And then for the steel, we would do the same thing. We would say that plus that times that quantity squared. And so for the steel, that comes out to 7752.38. And then for the concrete, it comes out to 2800.91. So that's in inches to the fourth. But then we sum that up. And so when you sum that up, you should get 10,553.29. That's in inches to the fourth. So therefore, our cracked moment of inertia is 10,553.29 inches to the fourth. All right. Any questions? Again, I flew through that a little bit, but we've done that before, so I didn't think that would be too bad to go through a little bit expeditiously. So what we can do now is we can now compute our effective moment of inertia. Okay, and in order to compute this, let's just summarize the four quantities that we need to do this. So we need a cracked moment of inertia, which we computed to be 67.24 foot kips. We need an MA, which is 140 foot kips that was given to us. We need IG, which is 22,963.5 inches to the fourth. And then our cracked moment of inertia, which is 10,553.29 inches to the fourth. And so right off the bat, you should see these quantities, and looking at your IG and your ICR, first off, that's a check to see whether or not you've done everything correctly, because your cracked moment of inertia should be less than your gross moment of inertia. I mean, once the beam is cracked, it's weaker, so you should have a lower I as a result. Also, when you look at your MCR and your MA, your cracking moment is 67 foot kips, and your applied moment is 140. So some of the beam is cracked and some of it isn't, and that's only going to be the case if MA is higher. If MA is less than 2/3 of the cracking moment, we just don't worry about it. All right. Now with that, we need to plug and chug into our effective moment of inertia, the formula, and then that formula is as follows. Okay. So we have a fraction. The bottom of that fraction is 1 minus, then we have 2 MCR over 3 MA squared, and then 1 minus ICR over IG, and then on top we have ICR. That formula is taking a little bit of getting used to for me, because again, that formula is brand new. Last year it was a lot different. It was actually a little simpler last year. With the new code, the formula got a little more involved. All right, so let's just do this bottom. So 1 minus, let's do that in brackets, 2 times 67.24 foot kips, and then 3 times 140 foot kips. So right there, the units are going to cancel. That term is squared. 1 minus, and then on the cracked moment of inertia, we have 10,553.29 inches to the fourth, and then 22,963.5 inches to the fourth. So that does units cancel as well. So the only units we're left with are the units from up top, which is in inches to the fourth, 10,000. 553.29 inches to the fourth. All right, since this part's new, I'm going to request chat. I want y'all to compute this out, and I want to see what chat's getting as an answer. I got the answer right here, but I want to see what y'all are getting. We'll say to the nearest whole number just to keep it simple for y'all typing it in chat. I'll give you all a minute. That's not quite what I got. I got a little bit of a different answer. Huh. Okay. Now, what Farrah got, that's what I got. That's the value I got. I got 11172.26. And what Jeremy got as well. That's what I got. Yeah, this formula it's not super difficult. I mean, we've dealt with more complicated formulas, but it's definitely one more complicated than last year. Don't forget to square the fraction, or that fraction in the bottom. I see. Okay, sorry, I read your number incorrectly, Mike. I think I transposed some digits. Yours was pretty close. I think it was probably just rounding. Mr. Toller, it might be rounding for you as well, but I don't know, that seems a little high. Okay, good. Sorry, Mr. Schwartz. I think you probably computed it correctly. It was just rounding on your end. So just to summarize the problem asks for two quantities, EC, which we computed EC way early on in the problem, and it was 3605 KSI, and then IE, which was 11172, we'll say 0.3 inches to the fourth. Okay, that's the answer. All right. All I'm concerned with today is your ability to compute those two quantities. Don't worry, we'll use them on Monday. Or sorry, when we come back. Sorry, not Monday. We'll use those on Wednesday. But that's all I'm concerned with today. I want to pull the homework up before we close it, just to highlight that. Give me 1 second. This has got to load up. Oh, I opened the wrong one. Hold on. Sorry, hold on. Okay. Okay, so this is going to be your homework assignment. Again, it's pretty much the exact same as what we just did. I do have to change something here. I just noticed, so I'm going to go ahead and do this. We're going to assume lightweight concrete with a unit weight of 120 PCF. I just realized you needed that value. So the only thing different with this problem is you're going to use a different formula for EC. And the second thing that's different is that you actually have to compute the MA. Other than that, it's pretty much exactly plug and chug as what we did before. The only other points I would make are, one, don't use any load factors. You just use the raw loads as they're given. Don't try and do 1.2 dead or 1.6 live or any of that. Again, this is serviceability. That part doesn't really matter, okay? So just the raw loads. And two, you're going to use WL squared over 8 for that distributed load, but you're not going to use WL squared over 8 for that point load, that P. You don't take that point load and try and convert it into a distributed load. That doesn't work. If you go to the slides, you'll actually find the formula for that point load. So it's going to be WL squared over 8 plus something, okay? And so that's going to be your homework. Other than that, it should be pretty plug and chug. Oh, I noticed that your D distance also got cut off here. I'll fix this and upload this. I believe D was 25.5, but don't worry, I'll fix this and re-upload. It'll become available at 11 a.m. and by then I'll have all that fixed. So so any questions? Let me go to chat. I'll give you all a minute to see if anybody has any questions. But it's not 11. It hasn't become available on Blackboard. I still have time to fix it. We'll say minus 1/10 of a point though, just for posterity. Any other questions? All right. Well, I'm going to go ahead and stop the recording and stop the share. For those of you in Steel, I'll see you here in a few minutes. For everybody else, y'all have a wonderful weekend. We'll see you on Monday. I'll try and get the review slides for the exam posted by the end of business today so that you all have time to review them. Again, I'll tell you the same thing that was Steel Design. It's going to be open notes and whatnot, so you don't have to make a formula sheet. I'm going to stop you if you want to, but everything's going to be available on Blackboard, so you won't have to worry about that. That's all I have, everybody. You all have a wonderful weekend for those of you who aren't in Steel, and for those of you in Steel, I'll see you here in a couple minutes.